Welcome everybody. Welcome to lecture 9 in algorithmic analysis. So in this lecture I will discuss uh, sorting in linear times algorithm. So again I am using Dr. Lee's slides, and I would like to thank her again for letting me use her slides. And as usual I will focus on mostly book, and I will explain the algorithm in my own ways. So let's go to the book content. Okay, so if you go to the book content, you will see that in chapter 8, so the authors discussed three linear time sorting algorithms: counting sort, radix sort, and bucket sort algorithms. Okay, so in this lecture we will mainly discuss counting sort algorithm. Okay, so this is a pretty linear time sorting algorithm. You will later understand why did I say pretty. It's not actually complete linear time sorting algorithm. And then later in the next lecture you will see how this counting sort algorithm is used in radix sort and bucket sort algorithms. Okay, so if we go to the book chapter, actually, then you will see this chapter is not a very large chapter. It is very like only a few pages. Okay, but so here only a few pages, actually up to here is counting sort algorithm started here, and after that radix sort. Okay, only that means only a few pages. Okay, so but before starting the counting sort algorithm, the author they discussed some related topics, that is is called a binary, is a linear, it's called decision tree. Okay, so as you know that a decision tree is a binary tree that has two sides. Okay, so left side and right side, left child and right child, and as usual so by comparing in a binary decision tree, only the operators, so the relational operators greater than, less than, greater or equal to, less or equal to, or these are used. Okay, so mainly the is a few, only the few relational operators are used: greater than, less than, greater or equal to, less or equal to this. Okay. And then a tree is formed. So at the root, these are the these are the root level, leaf level of a decision tree. So in the root leaf level we got a sorted sorted leaf, the one of the sorted leaves. Okay, so we will come back here soon. Okay, so let's discuss the relevant some information, that as we know so far, right? So what is the best or efficient sorting algorithm that so far we discussed? The merge sort, right? The merge sort and the heap sort are the best sorting algorithms that takes big O n log n time, right? So we discuss, although that there are some other sorting algorithms like insertion sort algorithm that is widely used. Okay, so that takes n squared. Okay, so running time, and that quick sort algorithm that takes also n squared running time. So far that means merge sort and heap sort algorithms are the are the best algorithms, right? That takes n log n time. And as you may hear that So far, uh, still computer scientists and programmers and researchers, they are continuing a lot of research to develop linear time algorithm, linear time sorting algorithms, but still it is not uh, been developed quite or an complete linear time sorting algorithm. So far you may hear that I'm sorry. Okay, so so far, so we are discussing the merge sort and heap sort algorithm. These two are the best sorting algorithms, right? But we know that some of these algorithms are called in place algorithm. That means they do not take additional memory space, but some of these take additional memory space. Okay, but so far the algorithm that takes pretty linear time is n and root over lg, that means log with base 2 of lg n. Okay, so this is the people say that this is the most efficient linear time algorithm that so far it has been developed, but in this course we are not discussing this. Okay. Definitely here lg means log with base 2, so we mean that as lg. Okay, but we will see that in this chapter we will discuss a pretty linear time algorithm that is called counting sort algorithm, sorting algorithms. Okay, that is not exactly linear time algorithm, so but you will understand soon why do I say it is a pretty linear time algorithm. Okay, so before as I discussed that, as I mentioned that, so at the beginning the authors, they discuss some relevant topics, so especially the decision tree model. So you may recall that the decision tree models so is based on comparison, right? Comparing some elements. So all of the comparison related merging algorithms, comparison related algorithm like merge sort and heap sort, like these algorithms takes log n height, right? Their height is log n. Okay, so because since the height is log n, so they take pretty less time than insertion and quicksort algorithm. So so here this is the discussion, so I like you to go through this discussion if you want to understand more relevant topics. So one thing is that we will see that in this discussion the authors they discuss that for instance, if you have 3 elements in a list or in an array with suffix a1, a2 and a3, right? For instance here, let me try to draw it. Okay, so 3 elements a1, a2 and a3. So if you have an array with these 3 elements, okay, so here it is used only a1 and 2. These are suffix are used, okay, to make it nice. So at the end, so how many comparison will be needed? Okay, and then how many, these are called leaves. Okay, these are the leaves. Okay, actually it will get factorial of n, factorial of 3. So you will see there will be factorial of 3 possible permutation in input level, so that decision tree must have at least 6 leaves. Okay, for instance, if I have two numbers, let me give you so for 3 numbers, right, I may have like this: a1, if a1 greater than maybe a1, it can be greater or less than, okay, a2, a3, this one, or I may have a1, so a3, a2, then we may have I'm sorry, a2, a1, a3, a2, a3, a1, so I got 4, right? Then 2 more, right? So a3, a1, a2, a3, a2, and a1. So there are 6, 1, 2, and 3 pairs, right? Factorial of 3, okay, that means equal to 6. So there will be 6 different combination, so in an actual value, right? So whether when you, so the result will be one of the 6. So these are the 6 leaves, okay. So if you have 4 items, so then there will be factorial of 4, that means 24, right? If there are 24 leaves, so that means the tree is going to larger and larger, right? And messy it's going, right? And then if you have like 5, only 5 elements, then how the tree will be like large tree, right? Too many branches and too many leaves, right? For 5 elements, there will be factorial of 5 equal to 120 leaves, right? So that means so and height in this, the height will be the height for all this is the height for this leaf, and this is the height for this leaf, and this is the height for this leaf, and this is the height for this leaf. So actually, so that you see that, for instance, here height is 1, 2, and 3, right? And here height is 1 and 2, right? So the height, so here 3, right? So the height will some factors of log n, some not actually log n, some factors of log n, that means something multiplied by number, or at least log n, right? So so that means all of the comparison sorting algorithms or comparison algorithms, or any algorithms that need any comparison, will take at least log n times, and some linear times of log n, okay, in order to complete the sorting. So but still the decision tree model is better. Still the decision tree model is better than other sorting algorithm. But as we know that, for instance, although there are many sorting algorithms, that some of a few we discussed, right, in this so far in this course, but so far, so any comparison sorting algorithm takes, okay, this is the lower bound. So in log n comparison in the worst case, but okay, so let us go through this slide again. So this slide, as we mentioned that, so far the merge sort and heap sort algorithms, these are the best sorting algorithms, but soon we will see that counting sort algorithm that is better than this, but in some cases, not always. Okay, but among these sorting algorithms, so we saw that some algorithms are in place algorithms, right? In place algorithm means they do not take extra memory space, but some of the algorithms are not in place algorithms. So the efficiency of an algorithm mostly depends on the running time, but extra memory space is a factor also. It's a considerable factor also. Okay, so so if you go through these few slides, these slides they discuss about the decision tree and decision tree model. Okay, so as I already discussed this, so decision tree represent the comparison model made by a comparison sort. Okay, so so this is the thing that I discussed, and same thing it is elaborated here. So at the end, what we will get, you will get factorial of n lives, right? So okay, so here, so the take home message from these few slides is that any decision tree that takes sort n elements has a height. Okay, so in the worst case a height that lower bound. Okay, so n log n, okay, or more. Okay, so this is lower bound, so it may take this or more. Okay, at least this n log n. So here do I have the slides? Oh no. Okay, so here we saw that in some cases it takes here height is 2, but here height 1 2 3, and here height is 1 2 3. Okay, so now there are some lemmas. Okay, so there are some proved theories and lemmas. That one of these is to prove that factorial n is less than 2 to the power h. So what is h over here? H is log n over here. Okay, so now actually our main discussion will be counting sort. So let us see. So this is the proof, the lemma. You can go through this. Okay, so please don't follow this slide further. And then now I want to jump to the actual counting sort algorithm. Okay, so actually the thing is that although so far we discussed the decision tree, okay, but the counting sort algorithm is not related to the decision tree, or it is not a comparison algorithm. Okay, so no comparison is needed in counting sort algorithm. Okay, but then what do we need? So counting sort algorithm is the name as the name infers. Counting sort algorithm is based on count. Okay, so count. So what to count? The question is that what to count. So okay, the count is counting is I'm coming that's on. It is assumed that each number in the input element is an integer. Okay, so count how many numbers are there, and so in each what is that called, in range. Okay, so okay, one thing that is counting sort is not a comparison based algorithm, so then it is a counting based algorithm. So then my question is that how do we count that? Okay, before we jump into the counting sort algorithm, so let us think that, as in know that the running time of the counting sort algorithm is pretty linear. It's not actually linear. Okay, I said pretty linear, so soon you will understand why do I say pretty linear. Okay. So the counting sort, in a nutshell, the counting sort algorithm, it determines for each input element, for instance x, the number of elements that are available that are less than x. Okay, so this is the main important point. For any number x, we will count how many numbers are there that are less than x. Okay, so then as efficiently we can count for each elements how many numbers are there in the list that are less than that number, then our counting will be determined, and then from there we can sort, okay, the numbers efficiently. Okay, so the counting sort algorithm, so let me go to the book. Okay, so here, so the book, it describes visually how this counting is done, and for a set of numbers, given numbers. Okay, so I will discuss this soon, and but you can go through this. Actually, you need to, in order to understand the counting sort algorithm, you need to understand this. Okay. Okay, so you see that this is the counting sort algorithm. It is not too large. Okay, so I will discuss this counting sort algorithm. Okay, so let me do it side by side. Okay, so I cannot do side by side, but one thing is that the counting sort algorithms, it has an input array, and definitely it will give an output array. Okay, and the counting sort algorithm is not an in-place algorithm, so it needs some extra memory, another array. Okay, so for instance, the output will be put in another array, so this is why it is not called in-place algorithm. And all, in addition to that, it will need another temporary array that for counting. Okay, so in the temporary array, what do we count? In the temporary array, we will count the range based on the range of the element. Okay, so for instance, if my input array has elements 1 to n. Okay, another thing is that, remember that the counting array is a counting sort algorithm is applicable for only positive integers. Okay, it does not work for negative integer. Okay, so if you know that all of the numbers are positive, or that means greater or equal to 0, okay, then the counting sort algorithm is an efficient algorithm. Okay, and if the numbers are within a small range, then the algorithm will be efficient. Okay, so for instance, here, if the number are, okay, so between 1 to k, so k is the range. Okay, so the maximum number is k, friends. So let me explain to the book. Okay, so here, so the counting sort algorithm, it takes an input array E, an output array B. Okay, and the k is the range. Algorithm, it works only for positive integer numbers. So if in your input array, if there is any negative integer number, then counting sort will not be applicable. If there is a decimal number or floating point number, it will not work. Okay, so only if you have integer numbers, positive integer numbers in your array, then that will work. And later you will see, so you will understand that if the range is small, then your counting sort algorithm will be efficient. Okay. So and so you can provide this input array and k value in as a local variable or argument variable. Okay, both work. Okay, and then you can have it argument, or you can return it at the end of this algorithm. You can return b as an array. This method may return an array, or you can display the array. Okay, so that depends on the variation. So the first, let us say what do we need to do. So as you know that counting sort algorithm is not an in-place algorithm. This is why it takes another array, so that it takes some extra memory space. And also the counting sort algorithm, it takes another auxiliary array. So counting array, where do we count? So the auxiliary array, its size will be the range. Okay, k value. So what do we need to do? We need array A, array another array C, and another array B is the output array. So let me go to this. So let us go to this example with this code with this example. So let us think that we have an array or list with these 5 elements. Okay, so give attention please. If you understand this with these 5 elements, you will understand for any number of elements. So here, what is k value here? K value is here is 4. Okay, so the highest element. Okay, and one thing that, so for this book version, we consider that the support array, so it length will be still 5. It has 5. It has 5. Okay, so again, so this slide has a different version than the book. I want to explain you both so that you understand in both ways, and whichever is you feel comfort with, you can follow that way. Okay, so let me explain this one. So what happens? So initially, what is going for I equal to 1 to k. Okay, that means 1 to 4. So we are initializing the C array with all elements 0. Okay, so that means initially all elements will be 0. The first for loop is done here, right? The first for loop is done. Okay, then what we are doing here, okay, so the second for loop here. For the second for loop, what is you doing here? For j equal to 1 to n, how can I find the n? N is the array length, initial array length, right? That means a of 1 equal to, we get 4. So then what we are doing, so once we get a 4, and then on the fourth place in C, as soon as we get a 4 over here, any element, okay, so 4, so then we are increasing this by 1. So 0 is increasing by 1, right? Okay, so then we are in for the next j x here in C, and we are increasing that by 1. Okay, so here 1. Okay, so then again here j equal to 3 and a of j equal to 3, then we are going to this third here in element in this array, and we are increasing by 1. Okay, so then we got, next time we got here j equal to 4, a of j equal to 4. That means we are going c of 4, we are increasing c of 4 by 1. That means what we have got over here, we got another 4, right? Another 4 over here. So initially there was 1 4, and then now we got another 4. so that means we are increasing this by 1 again. Okay, so then now over here next we are next in the next iteration, j equal to 5, a of j equal to c5, right? So we are increasing. Okay, so a of j equal to 3, so that means c3, so we are increasing this c3 by another 1. Okay, this is why we got over here. Okay, so then now what we have got over here, so now we have got over here, what we have got over here, we see that C, this C array, it has value 1, 0, 2 and 2. That means we can see that there is 1 1 in the original array, there is only 1 1. Okay, and there is no 2. So you see that, is there any 2? No, there is no 2. Okay, and there are there are 2 3s, 2 3. Okay, so this is 1 3 and this is another 3. Okay, so there are 2 3s, and there are 2 4. So you see the 1 4 and you see the another 4. Okay, so at the end of the second, this is the second for loop, right? This is the second for loop. At the end of second for loop we got, so how many numbers are there? You see that there are 5 numbers over here, right? So you have 5, 1 3, 1 plus 2 3 and 3 plus 2 5 numbers. Okay, but it will say then there is 1 1 is on exist 1 time, 2 exists 0 time, 3 exists 2 times and 4 exists 2 times. Okay, now you should understand the second for loop. Okay, the second, this is the second for loop is gone. Okay, so straightforward. Okay, now the third for loop. Okay, so the third for loop, what does it actually it reshuffles the C. Okay, the auxiliary array, it reshuffles the auxiliary array. How does it reshuffles? You see that it says Cj equal to Ci for I start from 2. Okay, second next element, it says the Ci equal to Ci plus Ci minus 1. Okay, so let me go to the okay, slide over here. So this one, right? So it start from the this here over here. Okay, so this actually from start from here, this. So what it does, it add up cumulatively. Okay, let me explain this. Rho equal to 1. Okay, and then then so that means 0 will be replaced as 1. Okay, and then here what do we have? 1 over here, right? So the 1 plus 2 equal to 3, right? So here we got 1 over here, instead of 0 we got 1 over here. Then this 1 will be added with this 2, then 1 plus 2 equal to 3. Just add up the previous 2 elements. Okay, in order to make the cumulative sum. And then after that, so then we have 3 over here, right? So then 3 plus this 2, 3 plus 2 equal to 5. Okay, so at the end of this modified C, what we have got? At the end of here, there is one element less or equal to 1. You see that there is one element less or equal to 1, right? And there is there are 2 elements. Okay, so there is also one element less or equal to 2. That there is only one element less or equal to 2, and there is 3 elements less or equal to 3. So this one, and this one, these 3 elements are less or equal to 3, and there are 5 elements less or equal to 4. So you see that 1, 2, 3, 4 and 5, these all of these 5 elements, these one, these one, these one, these one and these one, these are less or equal to 5. So that means this cumulative array will tell us that there are so one element less or equal to 1. So here less or equal to, there is these 3 elements less or equal to these 3. Okay, so this one comes here and these 3 comes here. Okay, and this means there exist 5 elements less or equal to 4. Okay, so what we will get at the end here, okay, so at the end of third for loop we will get a cumulative array. Okay, the array with the cumulative element that will tell us that how many elements are there and what are the shapes of the elements. Okay, now let us jump into the last for loop. Okay, the last for loop is a little bit difficult to understand sometime. Okay, but if you give focus then you can understand. Okay, the last for loop, you see that this is the complicated part. You said b of c of a j. What is j equal to over here? J equal to 5. For pseudocode j equal to 5, right? What we are doing over here, okay, so we are finding j. What is j over here? Initially 5, right? So then initially what we will do, aj, right? So in the last for loop what we will do, we use input array, and with the help of the modified c, actually we have only on c, so don't mislead it that it is another array. This is the same c array. Okay, a modified one, cumulative one. Okay, so then we will use array a. With the help of c we will make our final output array. Okay, so how do we do that? So this part is difficult. This is b of c of a. So what does it do? So let us understand. Okay, so aj, that means a5. So a5 is the element, it gives an element, right? So then j is 5, this is index, so a of j will give us 3, so we will get 3. Okay, so then 3, this a of j is equal to 3 will be used for c, the as the index for c. So c 3. So what is c3 over here? So 1, it starts with 1, 3 and 4, right? So c3 will be 2, right? c3 we got 2, right? So then what we will say, so then we got this 3. This 3 will be put to c3. What is this? c3 equal to 2, right? Equal to 2. Okay, so this, now we are going b2. So then here b2 over here. So at this position in b2, what we are putting over here, the value 3, aj. Okay, the value aj means 3. So that means at position 2 in B, or our output array, we are putting this value. So that means here, although it is a little bit complicated, okay, so you can rewind this. So that means this 3 will go its position, actual position in 3. Now, so what is this value? C of 3 equal to 2, right? We are decreasing 1 by 1. Why do we need to decrease? Because we have already inserted one value, right? So we already moved one value over here, so this one will be 1. Okay, now okay, so now it will go similarly, it will go for j equal to 4. Okay, so then when it goes for j equal to j equal to 4, okay, so then at this point what it will do, a of j equal to a of 4 equal to 4, right? A of j, this will be 4, and c of 4 equal to 4, right? So it start 1 2, it has 2 3 4, c of 4 equal to 4, and then b at b4, that means at b4, so that means it will go, it will get 4, it will get 4, and then c of 4 will be 4, and then at b4 this value will be pushed in here in b. Okay, so the 4, that means a of 4 equal to 4, right? And then c of 4 equal to 4, that means at b of 4, that means at b of 4, what value will be pushed? aj. What is aj? Equal to 4, right? 4 value will be pushed to here, 1 2 3 4 number here. Okay, and then over here a of c of 4 will be decreased by 1, because one value we moved already over here, right? So this value will be 3. Okay, so by this way, so what it will do, so it will move all of the elements. Okay, now if we see the complexity of time complexity of counting sort algorithm is pretty simple to calculate. So this part it takes k, right, theta of k, and this part theta of n, and this part theta of k, okay, and this part n, right? So here the total time complexity is theta of n plus k. Now what is k? Is the range, right? So if range is pretty small, then the time complexity of counting sort algorithm will be pretty linear, right? But if you have one in a list, if you have one value like 1 5 and another value is 5,000 or 500,000, is very large value, right? So then means your k will be very large number, right? Very large number. So in that case k will be dominant, right? So here it gives us linear. So if n is way greater or equal to k. That means if k is pretty small, that means if the values are within a small range, then it works pretty efficiently. Okay, now so the time complexity of counting sort algorithm is pretty linear. You understand that in case of small k value, but in case of large k value it is not linear, and then it is not efficient. And another thing is that you will see that it does not work for any negative numbers. So now, as I discussed, I will go through the algorithm that is defined in the book. So in the book it says k I equal to 1 to k, right? It's no problem. So it has k value, so that means you will assign this for this book version of this algorithm. You will have your C array will be 0, which is index from 0, 1, 2 dot up to k. Okay, and then it says so this is done, and this is same thing. And for your array, A array, right, over here. So A array, we start with, since this in pseudocode format, we start with A array, we start with index. The book discussed with index 1 to n, 1, 2, 3 up to n. Okay, and then B will be same thing, n to 1, that means 1 to n. So B will be 1, index 1, 2, 2, 3 to n. Okay, so other than it, everything is same, but now I think still it seems to be complicated. You may not understand clearly, so now let me explain this with a live program. So if we go to my Replit account, so then in my Replit account I have counting sort algorithm example. Okay, so I want to explain how you can implement your counting sort algorithm in a live program. So this code is written in Java. You can convert it in C++ or C# or any other language quickly, as if you understand those languages. Okay, so the main method over here is counting sort method. It takes 2 arguments, okay, integer input array, and k is the range. Okay, you can provide k as a parameter, or you can declare k as a local variable, no problem. Okay, so here n is my input array dot length, okay, over here, and then the output array will be same length, right, for as the input array. So output array will have n. Okay, so now this is the first loop, for loop. Okay, so what we are doing over here, we are declaring a count, that means C array. Okay, so same type, so integer type array, so integer type with k plus 1 over here. Remember that k plus 1, you must make it as k plus 1. If you make it k over here, it will not work. Okay, so here, so initializing, we are initializing the count array with all elements initially 0, right? Initially we are making this, initializing the count element all as 0. Then what we are doing over here, so this is the second, so this is the first for loop, right? Okay, in the book. So let me make it side by side. So this is the first for loop. Okay, the first for loop is here. This is the first for loop. Okay, so second for loop is over here. Second for loop is here. Okay, so so this is the first for loop. So the implementation of first for loop is here. Okay, the second for loop is here. So j equal to, or you can say I or j, no problem. Okay, so you can say I or j index variable. So it's equal to 1 to length, or in my program code I said actually program in actual programming languages array index start with 0, right? So we say 1 to 0 to I less than n. Okay, over here. But if you use pseudocode, then 2 length. Okay, but in actual program code length -1. So just we are increasing count array I plus count array I plus 1. Okay, this is similar to this. Okay, so let me change my color. So this is the second for loop is over here. Now this will be the third for loop. Okay, so the third for loop, this is the third for loop over here. You see these are identical. Okay, in the third for loop, what we are doing for so this is the cumulative. We are making the cumulative. Okay, cumulative counting array. Okay, so we are making, so for k I equal to 1 to k, I equal to 1 to k, that is what is your k over here. The count dot length, count array is the k array, so its length will be this k. Okay, so then count I equal okay, count I equal to count I plus count I minus 1, that's same thing. Okay, count I equal to count I plus count I minus 1, same thing. Okay, and this is the last. Okay, the last for loop. So this is the last for loop. This is the last for loop. So I can say this is the first for, and this is the second for, this is the third for, and this is the fourth for loop. So at the fourth for loop, you see that, and the implementation is it start from I equal to n minus 1. So in actual program code, since last index has the index n minus 1, right? So n is length over here. Okay, so this is why n minus 1, and then it will go up to 1 and it will decrease. And then what we are doing over here, the p is our output array, and then c is my count array. Okay, and a is my in here in array is my a over here. So then here, since we are taking from the last element has index, we need to decrease an index and length -1, and then we are moving this here, and then give attention of here this minus, that means we are decreasing this. Okay, so now, so you see that this is my the URL of my program code. Okay, so now if I go through this code is simple over here, and then what do I have over here? Okay, last one, just I'm moving the element from input array to output array. Okay, and this is the main method, and it has a print array elements, and it has the main class. Okay, the main class at print array method, and it has the main method. So the main method has an array with elements. Okay, so then what I'm doing over here, so since I passed in the my program k over here, right, so I need to find out k over here, the main one. So how can I find k? So k is the maximum value, right? And here k is the maximum value, right? So how can I find max value? It is a search algorithm, so I can do this search in linear time, linear search algorithm. Okay, so linear search algorithm, so I'm to find the max element. So the max element is my k. So I'm passing, I created an object of the counting sort algorithm, and we're calling the counting sort method, and this I'm passing this array and with max element. So what is max element over here? It is k, right? The max element is over here is k. That is the highest number. Okay, okay, but here this one thing, remember that we need to create the count with an extra one element. Okay, so k plus 1. Okay, the reason is that we consider this this counting sort algorithm that it works for index from 0. We may start from index 0, otherwise it will not work. So this we need to start from 0. Okay, so now if I run this program, then you will see that it works. Okay, so this is my unsorted array, and this is my sorted array. It is sorted in ascending order. Okay, you may trick this program to make it into display your numbers in descending order. Okay, but let us explore the sorting algorithm. Okay, so what we said that it will not work for any negative numbers. That means this is the question, that this algorithm is applicable only for positive integers. So if I have 0, then this will work. Okay, so 0 is not a positive, but it's not a negative number, right? So 0 can work, or it should work. Okay, so but if I have -10 or -5, it will not work. Why it does not work? Can you remember that? Why the negative number does not work? Think about a second. Because we use this one as in our k index array, right? So we use this number to find the range, okay, and the k value. So in the k element, k array start with index 0, and it cannot start with index negative, or it can be start from the minimum, from the lowest index. Okay, from the lowest index, it can start from lowest index, or it can start from 0, whatever you say, but it cannot start from negative index. An array cannot have a negative index, so it will not work. Okay, but if you have any large number, for instance, it will take long time, right? So then, but it will work, but it will take long time. So that means this algorithm will not be efficient in case of very large number. You see that it took some time to display. Did you notice that? Okay, let us give large number, but it should be within integer range. Okay, so it will take time for the large numbers, so that is why it is taking some time. Okay. So now I have another example of counting sort algorithm for character type array. Okay, so it is a little bit different. So in case of character type array, okay, so you know that whenever we use a character type array, the character, we need ASCII code for this character, right? This character value we need ASCII code. So this is why for character type array we can consider as the k as 256. So for ASCII code 0 to 255 is our ASCII range. So then you can add 1, 255, you can say actually 255 plus 1, right? You understand this way, that means 256, and then everything is same. So you can compare this. So this is an array, character array, and so I put CSITEd experts, and then at the end of the sorting it should give me the characters in ascending order. Okay, so this is the address of my this program, counting sort example 2 for character type. Okay, so you can practice this program and then you can copy this code in your account. Okay, so that's now for today the lecture, and then I will have another lecture from this chapter, that where I will discuss the use of counting sort algorithms in radix sort and bucket sort algorithms. Okay, so the radix sort and bucket sort algorithms, there are two other pretty linear sort algorithms. They run under counting sort algorithm. Oh, one thing maybe I forgot to tell you. Okay, the counting sort algorithm is not an in place algorithm, but it is a stable algorithm. Stable means the value comes first, it also the value, so the value comes first if there are multiple values with same values, multiple elements, same index. So the element that comes first, it places first in the output array. Okay, so that is the good thing for counting sort algorithm, and because of this property of counting sort algorithm, it is applicable in radix sort and bucket sort algorithm. Otherwise it would not be applicable in radix sort and bucket sort algorithm. So that means, what do I mean by and actually the stable, that means for instance I have 3, right? So for this the all value has 3s, but for instance these 3 in a special shape heart shape, 3, okay, and these 3 in a cloud shape. Okay, so then these in the output array, these 3 will come here, and these 3 will come here. The first one appears in the input array, will be appeared in the output array first. Okay, similarly if this 4 is originally placed in a square, in a circle, and this 4 is put in a square, then this 4, okay, in the output array. Okay, so this 4 will come over here, and this 4 will come over here. Okay, so this is an important property of counting sort algorithm. That means it is a stable sort algorithm, because that means the value which comes first, it appears first. Okay, and this is possible due to that we, in the last for loop, we are starting from the back, right, back of the array, from the last element of the array, last index of the array. So that is how it is possible. Okay, so that's for now, and you will have some quiz questions from these sorting algorithms, and after I post my videos from the radix sort and the bucket sort algorithms, then we will complete the sorting algorithms. So thank you so much, and you have a good day.